Assalamu alaikum guys. Today we are going to be start with the lecture number 5, design of a steel bridge. So in lecture number 5 we will discuss a design example of a steel girder bridge. So we are going to be solve the reference book, Dr. Zaid Ahmed Siddiqui, the author of it. From that book, chapter number 9 is regarding the design of the steel bridge, and from chapter number 9 we are going to be solve the first example problem, design example, that is regarding the steel girder bridge. Okay, so in our introductory lecture, lecture number 1, we have studied in detail about the type of the bridges, and in those we have discussed about the girder bridge, just the girder bridge or the steel girder bridge. So we are going to be solve that particular example. Before starting this example, you must have an idea about the steel girder bridge. Here for the steel girder bridge, the load path is that here the bridge deck is missing in this particular figure. So here let's suppose if the bridge deck has been placed over these steel beams, steel girders mainly, actually not the beam, the steel girders. So above the steel girder, first of all, you are going to be having the bridge deck. Okay, so bridge deck is responsible to carry the load at first. The moving load and all of the vehicular loads, dead loads are going to be coming on the bridge deck at first, and from the bridge deck the load is going to be transferred to the stringers. So these stringers are actually not like the interior one having the different dimensions and the exterior one have a different dimensions. These stringers are equally placed, and these are having equally designed also, and these are going to be called as the plate girders. All are going to be called as girders. That's why it is going to be called as steel girder bridge. So all of the longitudinal members placed to carry the load coming from the bridge deck, those are going to be called as the girders, steel girders. So here this is also a girder, this is also a girder. You can see in this figure for this particular bridge 1, 2, 3, 4 and 5 girders are placed that are going to be carry the load coming from the bridge deck, and you cannot see the floor beams over here. Okay, only the diaphragm has been placed just for the stability purpose. Here you can see in between, this is the diaphragm. So diaphragm has been placed in between at a constant spacing along the length of the girders, and you can see the transom. That's what I have told you. This is going to be called as transom. This transom is again a laterally placed member. So this whole structural element or the component is the transom. So your girders are going to be bridged or are spanned between these piers. So below the transom you can see these piers of this bridge, so or columns you can say, or the vertical component, those are responsible to carry the load from the superstructure to the foundation of the bridge. So here you can see the second pier, and here you can see the laterally placed transom. So your stringers are going to be put their load or going to be transfer their load from this contact point on the transom, and the transom is responsible to transfer the load towards the piers from all of the sides, and from the piers the load has been transferred to the foundation. So here you can see that there are no floor beams actually. So directly either your stringers are placed on abutments on both of the sides without the intermediate columns or the piers, or intermediately if the longer spans are there for the steel girder bridge, then you have to place intermediately the piers. So either your longitudinal beams like your steel girders are going to be placed on the piers or directly on the abutment. So here abutments are not there, just the intermediate part of the bridge has been constructed. So you can see this is the transom and this is the pier. So 2 piers has been shown over here. This bridge is under construction actually, so that's why and the girders are visible. That's why I have shared this picture with you guys, just to give you a better understanding about the steel girder bridge. So what are the structural components are left to be discussed? Only the bridge deck and the steel girders. So you can technically called these all girders as stringers. Okay, so 2 exterior stringers and 3 interior. So separately the exterior girders are going to be designed, I mean the load analysis is different as compared to the interior. So the load analysis for the interior stringers we have to done separately, and the load analysis for the exterior stringers we have to done separately. But we are providing the same cross section throughout, and we are going to be designing it as a plate girder. All of these are the girders. So mean the girder bridge mean you are going to be designing it as a plate girder that you have done already in your steel structure course. So you have to be design it by yourself at the end of our example problem. So these beams are there, so no floor beams are present, so just the 2 components mainly to be designed for the steel girder bridge actually. That's we are going to be start with. So this is example 9.1. The statement of the example 9.1 is given over here, that you have to design a single span steel beam bridge. Okay, so this is steel girder bridge or steel beam bridge. So generally we can replace this word with girder also. If anywhere you will see this word, so it will be the same. Steel girder bridge or steel beam bridge of span 12.250 meters with minimum edge to shear connections between the steel beam and the concrete deck slab. The curb to curb roadway width is 11.24 meters. So the roadway width is also given from curb to curb from both of the sides. So along the cross section the roadway width is 11.25 in lateral direction with 380 millimeter curb. So curb dimension is also given. After this 11.24 meter on both of the sides, 380 millimeter curb has been provided, and a barrier on each side. So mean the barrier has been also be provided, and you have to be include the weight for the calculation of the dead load, the weight of the barrier and the curb also. The loading is HL93. So the truck load and tandem load you are going to be include, and besides a wearing surface of 15 millimeter. So here fixed wearing surface thickness has been given to you. Provide allowance for 75 millimeter thick bitumen overlay. So bituminous overlay thickness has also been specified to you. So what you have to do, you have to just go for the thickness of the slab, and ultimately these thicknesses above the bridge deck slab you can add into it to get the total thickness of the slab. FC prime is 30 megapascal, Fy is 415 megapascals, and you have to use the structural steel A36. So all the values are given, those are needed to be start with our design. Now we can go ahead. So if we are going to start solving it, so first of all we have to, that will be very convenient for us to be solve it in different steps. So the very first step is that you have to be first of all finalize the arrangement of the steel beams regarding their spacing. This S value is very important to be calculated at first, because the number of the beams mean the girders and the in-between spacing is very important to be known at first. So first of all we are going to be decide about the overhang of the deck. If the exterior beam is there, that is like the exterior girder, you can see in the figure also. These two, let's suppose, are the exterior girders. So the exterior girder, the center of the girder till the edge of the bridge deck slab, that is going to be called as overhang. So that particular overhang is recommended by the ASHTO to be taken equal to 35% to 40% of the inner spacing of the beam to get nearly the same forces on the exterior and the interior beam. That is the reason and the logic behind that, that you are considering whatever the inner spacing are there. Let's suppose it comes out to be whatever the value is, this S is. At first, at start, we don't know about this internal spacing. So whatever the spacing is, let's suppose it is S. So 35 to 40% of this inner spacing in between the girders, this spacing, internal spacing, okay. So these are going to be considered as 35% of the 45% to be provided as an overhang outside on both of the side. Okay, so just to get the nearly the same forces experienced by the exterior, so you are not going to be experience the more torsional forces or the stresses. for this exterior beam. Otherwise, the difference between the section after the load analysis, mu and vu, if you get for you are going to be calculate for the interior analysis you have done and for the exterior analysis you have done, and after the load analysis, so both of the beams, interior and exterior, you will get a hell lot of difference in between the values of these two if you are not going to be considering this. So just to get approximately the same bending moments and the shear forces experienced by the interior and the exterior beam, we are going to be select this overhang of the deck as equal to 35% to 40%. Usual range of the stringers or the steel beam spacing is 1.5 meters to 3 meter. If the inner spacing are 4, so if this is the usual practice by the ASHTO, that if the steel beam spacing is going to be considered between 1.5 meter to 3 meters, anywhere in between. So if this is the particular case, and depending upon that the inner spaces you are considering equal to 4, then the spacing of the inner beam S can be calculated by equating the estimated and actual values. So if you see from the top of the bridge deck, these values are known to us. Okay, this value from curb to curb, this roadway width is given to us. Okay, so this is 11.24 and 11,240 millimeters. We are well known with this value, and this curve is equal to 380 millimeters. So on both of the sides you are going to be multiplying it with 2. So 380 just coming from the edge of the curve down, so this will be equal to 380 millimeter. So you can see this figure over here, from the curve edge to from the exterior side till the edge of the exterior edge of the deck slab. So this distance is equal to 380 millimeter. So if you will going to be see with respect to the roadway width, then from the edge to edge distance, this total distance is known to us. Okay, so keep this known distance on one side of the equation and keep unknown on the other side. So unknown means that this overhang part, unknown means we don't know about this overhang part on both of the side from the center of the exterior girder, and we don't know about the spacing at first. So let's start with assuming the inner space is equal to 4, then the internal spaces are 4, so total number of the girders will be 5. This is the first spacing, this is the second spacing, this is the third, and this one is the fourth one. So what does it mean? The total number of the girders will be 5. Okay, so it will be the spacing are 4 into S. So 4 into S is going to be incorporate or going to be include all this distance from the exterior center of the exterior girder to the center of both exterior girders, in between distance. And 4S, 0.8S will be the 80% of, mean this 40% of the internal spacing overhang we are providing. Okay, 40%. So 40% on one side and 40% on other side overhang. Both will be 80%. So it will be 0.8 of the S. So this is the overhang part. This one is the internal spacing. So we are going to be equating both values, and from there unknown S can be calculated, comes out to be 2500. So this 2500 is within that particular range specified by the ASHTO, that is the general or the usual range considered for the string or the steel beams. So if it is not, mean if this S comes out to be equal to less than 1.5 meter or more than 3 meter, then you can revise this number, this 4. Okay, so if it comes out to be less than, then you are going to be decrease the spacing. If it is more than that, then you can increase the spacing. So in this particular way, both of the ways you are going to be revise the section. So rest will remain same, overhang will remain same. These are the known values. Only this factor 4 can be increased or can be decreased depending upon the values for the spacing in between the girders. You are getting the answer. So it should be between 1.5 to 3 meter. If not, then you have to revise it. Now, the conclusion of the step number 1 is that the overhang we have calculated this will be the 0.8 of 2500. Okay, that comes out to be whatever, you have to be right. And secondly, second conclusion is that you have calculated the spacing 2500 in between the stringers. Now second step is you have to design the concrete deck slab. So for that we are known with the slab depth formula, that will be S plus 3000 divided by 30 from the AASHTO table, and it should be greater than 175 millimeter. And that value is also very familiar, and by the AASHTO is given that the minimum deck slab. Also in the previous lecture number 4 also we have discussed in detail about the during when we were discussing about the design of the concrete deck slab, there we have discussed in detail. Okay, so 175 millimeter is the minimum deck slab depth used in design, and this is the actual formula. So whatever you are calculating by using this formula, inputting 2500 as S, and you are getting 184. If it comes out to be less than 175, you have to take it as a minimum equal to 175. Okay, take it 175 or more than that approximately. So NHS suggest is equal to 190. So generally we are going to be taking it as 170. So it is equal to 184. So whole number, take it, round it up to whole numbers, it will be 190 millimeter. Okay, so adding 15 millimeter for the varying surface, it's given in the given data, you are adding it up, and finally you are getting 205 millimeters. Slab depth for the overhang portion, that is 230 millimeter. You have to consider the more thickness at the curb or for the overhang part, including the curb thickness. That is going to give you you have to consider resistance against Coulombian force. That's what I have told you, because the barrier you have to be installed and going to be fixed at the overhang. Within the overhang part, the curb is there, so the curb can be used for the sidewalk design, the bridge can be used for the pedestrian load, can be used for the barrier loads. So for that particular case, the accidents can be happened, and the overhang part can experience the Coulombian forces, the impact forces. And to overcome these forces, to resist these forces, you have to provide a larger thickness for that. So generally more than that, more than 200, you are providing. 205 is the actual thickness for the slab, and for the overhang part you are providing it at as 230 millimeter. You have to keep this in your mind, because once you are going to be doing the load analysis for the exterior stringer, so for the exterior, of course, the slab thickness will be more. Then comes clear cover to the reinforcement. So on the top of the deck subjected to the wear, it will be 60 millimeter, and bottom cast in place concrete slab, it will be 25 millimeter. Here you have to be considered the table, and depending upon the situation, the corresponding values you have to taken from the AASHTO table discussed in lecture number 4. Then comes conditions for the empirical design. If you are going to be following the empirical method of the design, then again in the theoretical part we have discussed in detail about the list of the conditions needed to be satisfied. So one by one now, according to our example problem, we are going to be satisfy all these conditions that are necessary to use the empirical method for the design of the deck slab. So for that, number one is the effective span of the slab. Okay, so that should be less than 4.1 meter, so 4100 millimeter. That's was given. So that we can calculate it by using the inner spacing of the beam, and by the inner spacing you can subtract the assumed BF of the selected steel section. So till now the steel section has not been selected. So for that, what we can do, we can take the 10% of the inner spacing, that is also an assumed value generally practiced by the AASHTO. It recommended that if the design girder is not there at first, so to use the empirical method you can use the 10% of the inner spacing between the plate girders, and that is equal to 250. Is the total, so 10% of it, this 2500 will be 250. So that will be the assumed BF of the steel section. So you are subtracting it, getting the effective span of the slab, that will be equal to 250 millimeter. So this is less than 4.1 meter. So it is going to give an OK sign. You have to write it. Once you are going to be design your bridge deck by following the empirical method, then you have to be first of all enlist all of the conditions for the empirical methods, and you have to be satisfy all of these equations by placing this OK. Okay, that is very important. Okay, so this condition is OK, then only you can move ahead for the second condition. So this ratio of span to depth ratio, that should be between 6 to 18 millimeter. So you have to be again satisfy this. 2250 is the SE, effective span of the slab. 190 is the depth of the slab. You have calculated earlier in the previous slide, and it comes out to be 11.84. It is in between 6 and 18. So it is OK. Number 3, core depth. Okay, so this core depth is in between the spacing. Core depth is that from the top cover and the bottom cover you have to subtract. So here you have the top steel for the slab, and here you have the bottom steel. I think we have discussed in the lecture also. So this is the cover, top cover, and this is the bottom cover. So in between the top and the bottom cover, that is going to be called as core depth. So the empirical method says that it should be greater than 100 millimeter, and also we have discussed in the table by the H2 also. So it comes out to be 120 millimeter. So it is greater than 100. It is also OK. Both covers, top and bottom, 60 and 25. 205 is the total depth, including the varying surface, and you are subtracting and you are getting more than 100. Then come deck slab depth. So depth is only one parameter. This is 175 millimeter. You have to keep in your mind all the time. So it comes out to 190 millimeter. Already we have calculated it, keeping this limitation in our mind. So it is 175, 190 greater than 175. It will be obviously be OK. Overhang portion comes out to be 620. Okay, so plus 380, that is the curve, that is 1000 millimeter. So 680 is 620 is the outer side, and the curve dimension is 380, and total curve width is 380 millimeter. From one side it comes out to be 1000 millimeter, and you have to compare it with the 5H as what we have discussed in theoretical part. Okay, so it comes out to be 5 into 190 and 950 millimeter. So 950 millimeter is less than 1, I mean you are getting it greater than that value 5H. Whatever you are getting should be greater than 5H. Okay, so it is 1000 millimeter, so it will also be OK. If it is not, then you have to go through for the revision of this overhang part, because this 380 is given in the problem statement. You cannot change it, but this overhang part you can change it. You have considered this overhang by considering 40% of the inner spacing, so that you can change or the modify if this condition is not OK. If OK, then it will be fine. Then you have FC prime, 30 megapascal. Already we have condition for the empirical method, 28 megapascal. So it is OK. A minimum of the two shear connectors will be placed at a spacing of 600 millimeters center to center. That we will provide, so it will be OK. So once all of the conditions has been satisfied, then we can go towards these values. Okay, if any one of the conditions we have discussed in the previous slide are not going to be satisfied, you cannot use these values for the bottom layer steel and for the top layer steel. So if those are satisfied, then this steel values, area of the steel values you can use, and corresponding to that you can calculate the number of the bars and with respect to the spacing. This spacing maximum permissible value is 450 millimeter. That's what I think we didn't discuss in the theoretical part. So here you have to be in design example problem, you have to be pointed out. Okay, so both these spacing of the steel are less than the maximum permissible value of 450. Generally it comes out to be less than 450, so there is no need to describe. But if in any case if this spacing is more than that, so you have to be very careful, and you are going beyond that particular value. You want to, any designer comes and he says that I want to provide this area of the steel more than this minimum value. Okay, minimum is this one, so greater than that any value I can provide and I want to provide. And if someone is interested in providing the area of the steel more than this value, then this spacing comes out to be greater than 250. So the maximum value is 450, at least equal to 450 or less than that this spacing needed to be provided. Okay, so if this is the particular case, then in this particular diagram you can show, you have to draw also once you are doing it, or you are going to be attempt this type of an example problem in exams or anywhere in for your design problem, your design project. So for that particular cases, wherever one by one for each step the diagrams or the figures are given, you have to show all of the results in the schematic in the form of schematic diagram likewise. So here you can see the bridge deck, and the top steel has been placed. So this is number 10 at 250 center to center, and for the bottom steel it is number 13 250 center to center, both longitudinally placed steel and the laterally placed steel. So this is the cross section. So for the cross section, this is the laterally placed and these are the longitudinal placed. This is one stringer, one girder has been shown. So on both of the sides, anywhere in between. So here you have the continuity sign and here you have the continuity sign, just to be show more prominently the steel, okay, within the bridge deck slab. So total depth you have to show, that is equal to 205, including the bearing surface and the bituminous layer. So this is 205. So that's what you have to be providing, the top layer steel and the bottom layer steel. So for the number of the lanes, it's very simple formula. You have the roadway width from curb to curb. So in between 3600 is the minimum criteria, and that comes out to be 3.12. So here you have to be very careful. That's what we have discussed in theoretical part, that only the integer part you have to take out. Let's suppose this value comes out to be 3.9. Okay, even 3.99. You have to be only take out the integer part. You are not going to be considering the decimal part of it. So integer value here also written in brackets very clearly. Okay, so if you are going to be considering it as 4, so it will be wrong. Only the integer part is considered as the number of the lanes, that value 3. So you are taking out the integer part and taking it as your answer for the number of the lanes. So that you are going to be at later stages, you can take out the multiple lane factor from the table depending upon the number of the lanes you have calculated in this particular step number 3. So keep this answer, you are getting 3 number of the lanes for the 11.24 roadway width for this particular bridge. Okay, so total 3 number of the lanes. Then comes multiple presence factor number 4. So for the 3 loaded lanes, multiple presence factor is 0.85. That's what I have told you. So wherever now hereafter it is needed to be use the multiple presence factor, you are going to be use this 0.85. So corresponding to 3, you have already the table for the multi-lane factor. Go there, okay, and take out and select this value corresponding to the number of the lanes 3. It will be 0.85 loaded lanes. Okay, so keep this multiple presence factor with you. Later on we will use it. Step number 5, dynamic load allowance. So that's what 33% of the design truck and the tandem, excluding the joints. Okay, just in between. So that is an extra information, but 33% for the design truck and tandem, and for excluding the joint and the fatigue, for which the value is different. Okay, so that's what actually this is out of scope for your case. That's what, but actually you have to be keep in your mind that if the particularly fatigue analysis has to be done, and for the joints, the extension and the contractions you are including, then there will be another criteria. But you are only interested in truck and design truck and tandem loads, so for that you have to use the dynamic load allowance factor equal to 33% of this value. Okay, so whatever you are getting by the load analysis, design truck and the tandem value, load value, moving load value, for that particular value you have to multiply this 33%. And for the lane loading it is 0. And also in the theoretical part we have discussed in detail that your load allowance, dynamic load allowance, is not applicable for the lane loading. Now once all of the factors are with you, we can start with the lateral distribution of the loads. The step number 6 is going to be incorporate the distribution factor. So in the theoretical part in detail we have discussed that why you are using the distribution factor. This distribution factor is for longitudinal members. Here in this particular case all are the plate girders. So what you have to do, you have to do the lateral distribution, live load distribution of the loads, distribution for live loads. Okay, so for the live loads you need to be perform the lateral distribution. This for the lateral distribution you need this factor G. Okay, lateral distribution factor that you are going to be multiply with the moving vehicle values to get their effect in the longitudinal direction. So the lateral directional effect has been transferred in the longitudinal direction, and then the longitude you are going to be placed this load by multiplying it with the G on longitudinally, and then you are going to be calculate by using the ILD, I mean the maximum effect for the moment and shear. Okay, so for starting with this two type of the distribution for the moving loads, lateral distribution and the longitudinal distribution, we need these steps. So very first step is the to calculate the distribution factors. And the last lecture number 3 we have discussed about the equations used to find out for the one design lane loaded and for the design more than one design lane loaded. The formulae are different to calculate the G. Input data is required only the span, mean the internal spacing of the stringers or the plate girders, and the total span. Span is given in the data, that is 12.250 meters, so 12,250 millimeters, and the internal spacing is 2500. So for that particular case the G formula is given. So for the initial, here also the kg and lt s cube needed to be determined. So we have the range of it. If you will remember in our theoretical part we had the range for this kg value, lower and minimum. For the initial proportioning and for the initial designing, what we can do, we can use it as equal to 1. Okay, so this 1 is going to be considered, if you will see those values, so this one value is approximately the average of both. Okay, extreme values, negative minimum and maximum, this one is considered as an average. So for the initial design for the beginners, so we are not going to be go in detailed analysis, mean the stiffness calculations and their proportions and then calculating those parameters. We can take it as equal to 1. Okay, if any you can say suitable or the logical conclusions for the design doesn't comes, then we can go for the other values less than that and more than that, and we can go for the actual design. Okay, the actual analysis values. But for the initial or for the beginners, it is recommended that you can consider it at equal to 1. So here also we are taking this whole component as equal to 1, this ratio of kg over LTS cube equal to 1, and rest values s and l is known to you. Input this in this equation and you can get this G distribution factor for one design lane loaded. Keep this value with you. Then 2 or more design lane loads. So here also the formula is given. Again you are considering it equal to 1 and you are getting 0.741. Out of these two or more design lane loads loaded and the one design lane loaded, you are getting you are taking out the maximum value, larger value. Okay, so previously it was 0.6 something, now it is 0.741. So 0.741 dominates. Okay, so the larger value dominates for the distribution factor. This distribution factor is for the lateral distribution of the live loads for the longitudinally placed girders or the stringers. Then for shear, one design lane loaded, formula is given, it is 0.689, and for 2 or more design lanes loaded it is 0.80. So again for the more design lanes loaded, this factor is the dominates. So G is equal to larger of these two, 0.840. So keep these two values with you for shear and for moment. Now for the exterior girder, for the movement, one design lane loaded. So if you remember your theoretical part here, we have written that we are going to be use the lever rule. Okay, so and also I have told you this is the simple mechanics rule, in which simple mechanics rule, engineering mechanics rule, in which you are going to be consider any point as in pivot, and you are going to be calculate the unknown value with you. Okay, so for the exterior girder, we are going to be, first of all you have to plot a figure with all of the known distances and the load. Okay, so here you can see simple the tandem load. So by the H toe, it is recommended that the wheel load, whatever the P value is, if the laterally placed, then half of the wheel load, mean P by 2, is come on axial load. आप इसको कह सकते हैं, you can say this P as an axial load. So if the axial load is whatever it is, so half of the axial load come on the lateral direction. Okay, in this particular direction, half will come in the third direction. In the this lateral direction, the one wheel has been placed and second wheel will be on the other side. So mean half load coming on this side and half load coming on the other side. So that P by 2 is needed to be considered for your exterior girder. And then the internal distance is fixed by the H toe. It is 1.8 meters or 1800 millimeters. Okay, this 600 meter is also recommended by the H toe. If you will see the lecture number 1. Okay, so it is recommended that whenever you are going to be place your wheels from the curb, so from the edge of the curb, this distance for the exterior part, that should be equal to 600 millimeter. Okay, and for in between from the lanes, in internal lanes, it should be 1.8. Okay, that we have discussed. So here it is 600 millimeter or 0.6 meters. Okay, so we have the girders. So place the girders. This is your first girder, exterior girder. So this overhang we have calculated equal to 620 millimeter, and this curb distance is also barrier and curb, it is 380 millimeter. So barrier is a part of the curve, mean from the curve you are just increasing the thickness and then you are adding a curb fence into it or barrier into it. Okay, so 380 millimeter, that's what given, and that's we have calculated 620, 40% of the internal spacing, and this 2500 is the internal space. Okay, and finally if you are going to be including the 600 plus 1800 and the second wheel coming in between. Okay, so rest of the value starting from here till here, okay, rest of the distance will be 720 if you are going to be adding up 2500 plus 620 plus 380. Okay, so it will be 1800 plus 600 minus all of this distance, so rest will be 720. Okay, so this is not the fixed value 720 is, you can calculate by subtracting 1800 plus 600 from 2500 plus 620 and 380. Okay, so this rest of the value will be, the distance will be 720 from this point C. This point C or the pivot point is going to be considered to be selected at the first interior girder. Okay, this pivot point, this C point is the pivot point about which you are going to be calculate the movements. Okay, actually what is going to be happened, this will be going to be act as a beam. Let's suppose if you have a beam and this beam is supported on two stringers. Okay, actually this is slab, but you can compare it with the situation when your beam is resting on two supports, okay, like your stringers. So what does it means? That the reactions are needed to be produced over here. Okay, so one reaction at one support and second reaction as second support, and the loads may be anyone. Here it is P by 2 vehicular load. Okay, so here P load or P load, half of it as vehicular load is there, then half we are considering, but let's suppose it is P. Okay, and you need to calculate these reaction for the exterior girder. That's why we have considered the pivot point as the first interior girder, so that all of the loads passing or the reaction going to be passed through it and unknown will be on the exterior, because this analysis for the exterior girder. So we need to see the effect of the interior girder, the load applied just near to the curb and the barrier. What is the effect of all of these loading on the exterior girder? If the interior will be there, then it will be okay, half from this side, half from this side. But for the exterior, this is unbalancing situation. From this side you can take half of it, okay, but on the other side you have curb, you have barrier, you may have sidewalk, you may have this overhang part. This is also smaller distance as compared to this 2500. So this effect from this vehicular load and this curb and barrier will be different from coming from this side. So this total effect from both of the sides on this exterior girder is needed to be determined in terms of the reaction calculation. Okay, so for this particular case, the lever rule can be applied, mean this point, the interior girder can be considered as the pivot point, and the other side the reaction can be calculated. So R into 2500 on one side and P by 2 into 720, these are the distances simply to calculate the moments about point C. And you are getting this relationship. So this relationship is going to give you an intermediate interrelated parameter or the factor that will be 0.648 between the reaction and the applied loads. So mean under the action of these applied loadings, the exterior girder reaction, the effect of these forces on the exterior girder is going to be affected by this factor, going to be increased by this factor or decreased by this factor. Okay, so this factor 0.648 can be considered as the lateral directional live load effect. Okay, so due to this effect the exterior girder can be affected. Okay, so this 1.2 is the one design lane load for the moment for the exterior girder. That's what we have calculated. Okay, this is the simply the factor, that is the multiple lane factor, and you are multiplying it with 0.648. So 0.648 is actually the relationship between the R and the P. Okay, this factor that is going to be relate your reaction. So effect of the applied lateral directional vehicular load to the reaction created or going to be implemented or going to be resulted by the exterior girder. That's what we are going to be calculating over here. Okay, so that particular factor is multiplied by the multiple lane factor, and finally you are getting G equal to 0.778. For two or more design lanes load, you have to calculate your G by multiplying your interior, G interior that you have already calculated for the interior stringers with this small e value. Okay, so this small e value can be calculated by using this equation we have discussed in theoretical part, 0.77 plus dE over 2800, and it should be greater than or at least equal to 1. If it is less than 1, you have to take it equal to 1. Okay, so this is going to be including only one unknown parameter, this is dE. So dE can be calculated by subtracting 1000 from the 380. So it is 620, and already we have calculated 620 millimeter. This 620 millimeter, or directly you can use this as 620 millimeter. So this 620 millimeter should be within this particular range, minus 300 to 910. So it is, so it will be okay. So then you are going to be use it in this equation after satisfying this condition. So it is going to give you 0.99, and you have to take it equal to 1. Okay, so in this particular way you are calculating and you are getting your E value, that is 1, and the same 0.741 you are getting. Out of these, one design lane loaded and two design, greater one is 0.778 from one design lane load, that you have to be use as your final value for the movement. Then for the shear, already we have calculated by using the lever rule, same criteria, same answer. And for the two or more design lane loaded, you have to be calculate another equation will be different. Here you are getting 0.807. Okay, so here is no limitation for the value greater than or equal to 1. Whatever the value is you are using, it is going to be 0.678, less than this particular value. So if you are comparing these two, larger one is again 0.778. So 0.778 will be the G value for the shear for exterior girder. So now finally you got 4 G values, 4 distribution factors. Okay, one distribution factor for the interior, and for moment. Second one, distribution factor, to incorporate the laterally loaded moving loads, their effects. It will be again for the interior stringer, but for the shear. Then you have G value for the exterior girder, for the movement, and then the last distribution factor for the exterior girder, same, but for the shear. So you have to be at the end of this step, these 4 distribution factors with you. Now comes longitudinal distribution. Okay, so number 7, maximum central live load moments. Okay, so this is the maximum effect of the live load moments. So for that you are going to be using the HL93 H2 loading. So for that, standard axial load, okay, and the simple tandem loads. Okay, so you are using, so standard axial load will be 35 kilonewtons, then for the front wheel, and 145 for the other 2 rear wheels. So you are familiar with these. So in this figure the ILD has been drawn for the movement, and the distance between the wheels or the axle are 4.3 meters. These are specified by the H2. These value of the load and these distances between the wheels are specified. So what you have to do, in between this 12.25 span, you have to be placed longitudinally. This 12.25 is the longitudinally span for the stringer. So whatever you have done by laterally placed the moving load, that was the G factor you have calculated. Now longitudinally you have to place your standard axial load, and then corresponding to that you have to be use this. You have to find out the perpendicular coordinates or the ordinates, and these ordinates needed to be multiplied with the corresponding loads, and finally you can get your answer. Okay, so there may be a case that one of the wheel can get out of the span, and for just 2 wheels you are calculating it. Whatever, you have to move this wheel on right or left side of this whole span of your stringer, and you have to calculate the position where you are getting the maximum answer. For this particular case, solution is given, you have to do it by yourself. Okay, they have given the maximum value with this particular situation. Okay, so where you are getting 608.3 by placing the 145 kilonewton wheel just at the top, at the maximum ordinate L by 4. Okay, so at the mid they have placed, this is the maximum ordinate. So near to the maximum ordinates, if you are placing your wheels, those are going to give you the maximum answer. That maybe you are going to be remembered by the ILDs. So this maximum value 608.3 we get by solving this ILD. First of all, plotting this ILD for the maximum effect for the live load in longitudinal direction, and then by placing the wheels of the loads for the axial loads, and by multiplying each wheel load with the corresponding ordinate of this triangle that you have drawn for as an ILD, and then you are getting the maximum value 608.3. Similarly, for the standard tandem loads, 110 kilonewtons, 110, in between distance is always 1.2 meter. So that is fixed, given by the H2. So you are placing it again, preferably one wheel should be on the maximum ordinate. Okay, so that particular position is going to give you the maximum answer. You can change it, and you can also see by yourself that if any other location or position can give you the answer more than 607.8, you can also check it for that. But apparently it looks like okay. So 110 into whatever the ordinates are, so you are getting 607.8. This is the simply for the movement ILD, you are getting the maximum movement effect for the longitudinally placed your live load. So for the lane load, it's always 9.3. Okay, you are getting it as, so 9.83 is okay, but this is UDL, so WL square by 8. So W is always 9.3 for the lane load. That is also given by the H2. You are not going to be changed this factor. So 9.3 is the lane load. So L square by 8, you are calculating the movement by this W value. Okay, this is the lane load, uniformly distributed live load actually. So it comes out to be 174.5 kilonewton meters. Keep this with you. Then comes the maximum live load and the impact movements. So if the total movement is needed to be calculated, including the live load effect and the impact moment, mean the dynamic load allowance factor, then what you have to do, you have to be first of all take greater of the vehicular load, axial load and tandem load, whatever the movement you have calculated. Okay, if the movement you are determining the total movement, you are calculating moment effect, you are calculating by considering the live load and the impact moment factor, then what you have to do, the factor, you are familiar with that. I am again revising and repeating that particular fact. Your impact moment can be calculated by multiplying the dynamic allowance factor only with the vehicular load. Vehicular load we have calculated axial and tandem. Out of these two, whatever the larger value is, this is 608.3. With that you have to multiply the factor 33%. So this is 1.33. You are multiplying it with that, and plus you are not multiplying this factor with the lane load. Lane load is separately is going to be added into it. So it is 174.5. 0.5. So all of the movements for the live load, okay, within the live load you have to separate out the moving vehicular live load and the uniformly distributed live load. Why? Because only the dynamic allowance factor needed to be multiplied with the moving vehicular load. Then you are adding separately without multiplying it with the factor lane load, and whatever you are getting by adding up all of the movements by the live load needed to be multiplied. Live load, I am again repeating it, only the live load movements by the lane load and by the moving vehicular load. You have to be, this is the longitudinal effect. How to incorporate the laterally placed live load effect? That is by the lateral distribution. And what we have done in the lateral distribution, 6th number step, we have calculated the G factor. So from the list I have told you in the previous slide, you have taken out that particular G for the interior girder and for the movement you have calculated. That G factor needed to be multiplied with all of this, finally calculated or added up the movement. That will be 728.0. So what you have done in this particular case, in this equation, this whatever in the bracket, it is the longitudinal distribution of the live load, and out of the bracket G is the lateral distribution of the live load. Okay, and finally by doing all of these lateral distribution and longitudinal distribution, finally you are getting your movement for the live load 728.80 kilonewton meter. Keep this value with you to use for the design purpose. For exterior girder, similar you have to do MA and MT. Again, only the moving vehicular load you are multiplying the 1.33 factor, and lane load will be separately calculated. Exterior girder will give you the difference for the nothing difference. Okay, so if longitudinally placed, so tandem load and live load all will tandem, and the axial load will be the same. Okay, and also the lane load will be the same. Only the difference will be the G factor, laterally placed. Longitudinally placed, it will not going to make any difference, but lateral effect once we have been calculating in the previous slide, so where the G value, calculation of the G value, that criteria was different for the exterior girder. That's why we are getting the different answer for the G. So the G value from the previous list for the exterior girder, for the movement you have to take and multiply with this value. So this is within the bracket longitudinal distribution, this outside the bracket is the lateral. You are multiplying this factor by getting the summation of the movement, finally effect of the movement equal to 765.19 for the exterior girder. Similar you have to do for the shear, maximum central live load shear, for the standard axial load. Okay, so the shear ILD you have to plot, or this is 145. So you are familiar with the shear ILD. If not, then I am repeating. So this will be the maximum. One ordinate is here and it will be 0 over here. Okay, so one ordinate, so it's not needed to be drawn over here because it's obvious all the time. So 145 equal to 1 Here you can see this is 145. So what does it means? We are placing the rear wheel. You are inverting the axial load by placing the front wheel towards the lowest ordinates, okay, and gradually you are placing the larger load wheel on the greater ordinate, largest ordinate. So it is 1. So 145 into 1, 145 into this ordinate, 135 into this ordinate, and you are getting the answer equal to 249.5. This is the maximum possible position for the axial load, for the shear ILD. Similarly, for the standard tandem loads, it's 110, 110, 1.2 is the distance in between. So 110 is multiplied by with the one ordinate, the maximum ordinate for the shear, and on the other side it will be 0.902. This is also be the maximum possible position to get you the maximum effect or the answer for the shear for tandem loads. So out of the tandem and axial, the maximum you have to consider. Before that, the lane load, so it will be 9.3. W will remain same as what I have told you, but L by 2. So it will be W L by 2. Okay, this will be the lane load calculation, 57 kilonewtons. Now come to the maximum live load and impact shear. So impact shear mean that dynamic load allowance factor, you have to be used again for the shear case. So here again the same formula as the moment, but only you have to replace it with the corresponding values of the shear maximum of axial and tandem and the lane load separately. Multiply this dynamic load allowance factor only with the moving vehicular loads, and 0.840 out of the list I have told you. For the G factors, you have to take out the interior girder and shear. That G factor you have to be used. So this is lateral distribution, this is longitudinal distribution. Finally you are getting 326.62. For the exterior girder, similar you have to do, only the difference will be in G value. Then comes dead load forces. So dead load forces you can do by yourself. For the interior girder, figure is given. Asphalt paving is the separately 75 millimeter, 205 millimeter you are providing. Okay, this is the bituminous overlay. This is including the wearing surface 205 millimeter. So in between the inner spacing are given. So for this particular case, for the stringers, we are designing the stringer actually. Above the stringer, including the self weight of the stringer, whatever the dead load is coming on the stringers, that needed to be now calculated in 9th step. So for this, that we can differentiate our dead loads as the dead load from the deck slab and the girder itself, and from the wearing surface. Dead load of the wearing surface, DC mean that the dead load of the concrete part, mean concrete slab and the self weight of the stringer, and DW mean the dead weight of the wearing surface. So for this particularly, all of the densities are with you and you can calculate it, thicknesses are with you, you are familiar with this procedure. For the girder itself, at first actually we are designing it, so we don't know about the cross section. So 15% of the deck slab weight you can consider as the girder self weight. So it comes out to be 1.80 kilonewton meter. This is a simple, you can say, assumption you can use as in beginner. And then WDC will be 13.84. And if total WDC is with you, mean the for the deck slab and the girder self weight, then the movement and the shear you can calculate. For the wearing surface separately, 75 millimeter thick asphalt paving is there. For their density will be different, 22, and you are getting 4.13 kilonewton per meter. So for that, the movement and the shear separately you have to calculate. Similarly for the exterior girder, okay, so here you can see the figure is going to give you all of the corresponding distances. Okay, so here you have 380 from curb distance, 620 overhang, total is 1000 here in this particular part, overhang part, and then you have all these values. So here this is actually going to be show you this part. Okay, so here other than the wearing surface, if we talk about the center of the girder, exterior girder, that will remain the same on the right hand side. But for the exterior girder, Why we are calculating the dead load separately? Because on the right hand side, all of this material is going to change the dead load. So for that, deck slab will give you this particular you can say equation, and overhang part is calculated separately, barrier weight separately, girder self weight separately, and then finally WDC can be calculated. Okay, so list is little bit larger as compared to interior. If for interior only two parameters, deck slab and girder, but for the exterior this overhang and barrier needed to be added into it. So use this, okay, for your case. So 2.5 will be the internal spacing. For the overhang it will be 1, mean 1000 millimeter, and for the barrier it is approximately area directly we are calculating. This is 1.17. Actually, if the barrier design is with you, we are considering it as 150 millimeter, height any 3 feet, 2 to 3 feet. Okay, so considering, so with this approximation of the barrier dimensions, we can get the area 0.17 millimeter. So by multiplying it with the area directly, 0.17 meter square, we are multiplying it with its density 23.5, its concrete density, and you are getting the answer. Then comes the varying surface. So similarly, for this, only that particular distance has been changed. Now the overhang part is going to be including from other side, so that is going to give you 3.21. okay, so you are getting your answer. Now finally we need this mu and vu. At the end of the slide you can see. Okay, for that we need the load combination equation, like our load analysis for the frame, for the beam, for the column, any other structural component. If the load analysis has been done for the concrete deck slab, for the varying surface dead load, for the live load and the impact factor considering it, if all of these movements in the shear you have already calculated, okay, then only need the load combination factors. Okay, so these factors are only be left with you. So this is the Ashto load combination equation for the steel bridges that is needed to be used. Okay, so if it is needed to be calculated movement, then you are going to be use the movement values correspondingly, and if shear is needed to be calculated, you are using the shear values. So this mu is needed to be considered as 0.95. okay, for all of the fatigue, all of the wind loading effects, earthquake effects, any other type of the soil effects. Okay, you may have the overlays on both of the sides on the abutments. Okay, you may have the humidity effects, you have any type of effects. Okay, in the online session I will make you clear. Okay, so any variant or invariant, when we go towards the specifications, in specifications you will see the load chapter, maybe second chapter of it, and in the load chapter you will see the type of the loading experienced by different type of the structures, and there you will see and you will observe that the mainly we can categorize the type of the loadings as variant and invariant. Okay, the variant mean those are going to give you the variations like wind load, live load, snow load, like this, and the invariant mean the type of the dead loads, type of the loads those are not moving as such. So live load are bilkul totally different, moving vehicular loads are totally different. Okay, so variant and invariant means static loads. So static loads and dynamic, in dynamic you may have the variant and you may have the moving vehicular loads. So all type of the variant type of the loadings, those are enlisted in specification, can be incorporated by using this factor mu. Actually this is 0.95. Rest moving vehicular loads and the dead loads we are considering in this bracket, but we are not considering the other type of the variant loads. So to consider the effect of those, we are going to be use this mu factor, because bridge is not a kind of structure that is ignored by these type of the loadings. Okay, wind loading, earthquake loading, and like this. So you have to be considerate, although the specific and the separate design is always there. Okay, but at first stage you need to be incorporate all of those variant loads into it. So those variant loads are going to be incorporated by using this mu factor. The rest is the factors 1.2 with DC, 1.50 with DW, and 1.75 with the live loads, and considering the lane load plus the moving vehicular load, and multiplying it with the impact factor. Then interior girder equation is with you now, corresponding all of the values calculated in the previous slides. Input over here, you will get your answer. Nothing is to be explained over here. So exterior girder, all of the values are with you, directly input taken from the previous slides, and input over here. Finally, out of these two, from interior and exterior, if it will be it would be the plate girder bridge, where the two exterior will be the plate girder and interior will be the stringers, I mean the smaller beams, hot roll beams you can provide, and the built up proper plate girders, designed plate girders you are providing at extremes as an exterior girder. Then you can use these values separately. Okay, but here you can see that this difference is very small, 1797 and 1630, and this difference is almost the same, you can say. Okay, so out of these two, the greater movement for interior from exterior interior, and the smaller you can use as final design movement and final design shear. Okay, so design moment and design shear is with you. Now you can use it to design your beam. So this is your assignment, guys, that after completing till that particular point, after calculating MU and VU for all of the 5 stringers, not the stringers, the girders. Okay, for all of the 5 girders you have to provide the same section. Okay, and that you are going to be provided by designing it. So by using this MU and VU calculated till last slide. So this is your assignment number 2. Assignment number 1 was the descriptive one, in which you have to be give the detail or the brief description about the steel bridges present within the Pakistan, our country. Okay, so at different locations you have to be the type of the bridges, and then their spans, whatever the mean details you are getting for the steel bridges present in Pakistan. That was your assignment number 1. Assignment number 2 is for example 9.1. That for the example number 9.1, you have to design the steel girder bridge. Okay, as in simple plate girder. So it will be girder bridge, mean the plate girder bridge. So all are the plate girders, all stringers are the plate girders, and these plate girders you have to be designed as you have designed in your steel structure course. Okay, on the similar pattern. So that was not going to be guided you guys. Okay, so not being instructed to you in any way, you have to do it by yourself. This is your assignment, do it, and the submission date will be announced later on.